In this video, I want to do two textbook problems as examples, problems 56 and 65 off of page 72. Problem 56 gives me information about three functions and asks me to evaluate limits using our limit laws, and number 65 is going to ask me to use the Sandwich Theorem. But first off, in problem number 56, I'm told that the limit as x approaches minus 2 of p is 4, of r is 0, and of function s is minus 3. I'm asked to evaluate these three statements. And we could probably do a lot of this mentally, but I want to use this as an exercise in using correct notation. So, the primary tool here is Theorem 1, or limit laws, that I can break up limits around sums, differences, I can pull out constant multiples, I have a product rule and a quotient rule for limits, a power rule and a root rule. So I want to go through part A here and just show you how to rewrite this limit using the sum rule. This statement is the same as taking the limit of each of the three functions and adding those limits together. This is what the sum rule really says. And now, because of that, I know the limit as x approaches minus 2 of p of x is 4. The limit as x approaches minus 2 of r of x is 0. And the limit as x approaches minus 2 of s of x is minus 3. So, in part A, I just get the number 1. This original limit is equal to the sum of these three limits is equal to the sum of these three numbers is equal to 1. The product rule for limits says I can rewrite this limit statement as the product of three limits. On this problem, again, we could probably have done this mentally, but rewriting it like this will help us on future problems. And again, now that I have the limits individually, I can replace them with their individual values. And of course, this isn't that interesting because I have three numbers multiplied together, one of which is 0. Finally, the quotient rule would tell me I could split up the top and the bottom. And have a limit on the top and a limit on the bottom. I'm going to need to move over to another board here. And so the first thing I want to do is rewrite that last statement. I could go on and evaluate this one because I know the limit of s of x was minus 3, but I'm going to work on the top first. I have a sum on the top. So I can rewrite that as the sum of two limits. Now, in this limit, I can pull out a minus 4. That's my constant multiple rule. And this one, I can pull out that positive 5, again with the constant multiple rule. And now that I have all three limit statements written with just the functions on the inside, I can replace them with their individual values. The limit as x approaches 2 of p of x is 4, so minus 4 times 4 is minus 16, plus 5 times the limit of r of x is 0, over the limit as x approaches minus 2 of s of x, which is minus 3. So we get 16/3 in part C. So there are my answers, 1, 0, and 16/3 for problem number 56 on page 72. The next problem I want to do is problem 65. Still on page 72. Problem 65 tells me that it can in fact be shown that 1 minus x squared over 6 is less than this expression is less than 1. Your author's not asking us to show this ourselves. He is telling us this is a fact and we can trust him. And then it goes on to ask, it can be shown that this is true for values of x close to 0. What, if anything, does this tell us about this limit? The limit as x approaches 0. The limit as x approaches 0 of x times sine x over 2 minus 2 cosine x. All right, well, this problem is under a heading that says the Sandwich Theorem, so I'm thinking we're going to use the Sandwich Theorem. But I want to provide some more context, because if we met this problem in the wild, it wouldn't necessarily say, hey, use the Sandwich Theorem. It would probably just look like this and say, hey, we need to find this limit. And so it's the inequality here that tells me the Sandwich Theorem is probably going to come into play. And I also notice that I have two limits. Or better said, I could take a limit as x approaches 0 of both of the bounding functions, y equals 1 minus x squared over 6 and y equals 1. Well, the limit as x approaches 0, this is a polynomial, so I can just substitute in. That's going to be 1. And then the top function, the limit as x approaches 0 of 1 is 1. Because of this, the squeeze theorem, or the sandwich theorem, implies that the limit of the function we just squeezed in the middle also has to be 1. When you're using the squeeze theorem, it's important to write down these two statements. You actually have to evaluate the limits on either side. You can't just guess it. But that's what the squeeze theorem does. I have a function that's bound between two other ones. If I can evaluate these easier limits, then I'll know that one. All right, those were my two problems. I hope that helps.